All right, I might get started, everyone. I will, because I've got a fair bit of content in this. So, my name's James Mitchell, and I'm going to be discussing today lessons learned from 2 decades of writing bad code. So, before we start, this is about my own personal journey, and all opinions are my own. And I'm going to ask that people try entering the questions in the GCAP app. So, in there, you can find the talk, and then there's a Q&A button in there. So I'm going to try it, and we'll see how well it works for questions. So, what is this talk about? So this talk's me trying to sort of convey the information I've learned over the years and sort of providing useful insights and that from the approaches that I've taken in software development. So, it's all started sort of back on an old Amstrad CPC 6128. This is it's a picture of not the original one that I had, but yeah, this is something that my family bought, I think, at a garage sale sometime in the mid-90s. It was already about 10 years old at the time, and we didn't have any discs or anything. No, it came with no programs, but it came with the book. And in the back of the book, there was a few little code listings, and sort of learnt to write BASIC through that. And my programming skills weren't that good at the time because I was still very, very young. But from that, I sort of moved on to building other things. And my first real project that I built was a bot for some different Half-Life mods called Agrobot. And it was based on an open source bot that someone else had built, I think primarily focused around Team Fortress Classic. So I was about 15 at the time that I wrote this, or modified the initial one. So it's very hacky. I think back on the code then, it was probably pretty awful at the time. It was. But progressing from that, sort of throughout sort of the early 2000s, I moved on to doing various different Half-Life mods, web development, and got into CTF challenges. These are sort of security challenges where you'll try and break into an artificial sort of system, reverse engineer things and stuff like that. And that sort of gave me a real passion for low-level programming. Did a little bit of system admin and sort of IT support things for a few high schools around the Bathurst area. I did, and then eventually decided I'm going to jump into games. So I went and did a games degree at AIE, I did. And then from there, met some people at Micro 4Day, started working at Micro 4Day just before they were acquired by Wargaming. And I was there for about 8 years, primarily working on the Big World engine. I was on server-related technologies because I had that sort of system admin experience, and that's sort of where it landed me. And then in 2020, moved to working at Sledgehammer Games, where I am now. And I initially started there in the online team before moving into directly engine work, which is where my real passion lies, it is. So the agenda for this talk, I'm going to dive into a little bit of my philosophy that I live by, which is always dive deeper into things, look under the cupboard, take a look at whatever you can, read documentation, everything. A little bit on performance, and then a little bit on software architecture. So let's jump into diving deeper. So let's say I'm writing a program and I want to sort of have, like my program enters a bad state. How do I make it terminate? So I'll think about it a little bit, and I'll remember there's an exit function I call. That's typically what I do in a project because I want to exit out of the program. So I'll write the code for that. If bad state, print out that I've hit a bad state, exit. I know the return codes are either 0 for it was success, or any other number means that it's not a successful run. So I test that, runs, it exits out when I do my testing. Someone comes to me a little bit later and, yeah, James, this seems to be hanging the program. So I go and try and do the exact steps that they've given me, and look at a call stack, and it looks like the call stack is doing some deinitialization of things. It's trying to shut down threads, and I just wanted to exit the program. I don't care what else was running or anything like that. So exit obviously was not the solution there. So I'll go and ask AI what I should do, because it's the new modern thing. So I ask it, I'm trying to exit from my C++ program. I'm calling exit, but it's causing destructors to be called and hanging my program. How do I avoid this? It comes back to me with this long, detailed answer. The main thing that I get out of that is I've got to call _exit instead, and that won't cause the destructors to be called. So thanks, AI. I'm going to go modify my code and call _exit instead. Yep, put that in. Now throw it up for code review, and someone will come along and say, what is std_exit? I think to myself, yeah, I don't really know. It's some new thing that I saw, so let me jump in the docs and dig a little bit deeper. So I pull up the C++ reference guide to S2D exit. Don't need to read this, probably a little bit small for everyone to read it here. But main thing that I read here is that it causes normal termination to occur without completely cleaning up the resources. And then I also spot in sort of this see also section down the bottom, there's another function, abort, that is actually for exiting when it does have a like abnormal state, which is really what I was after to begin with. The other thing that I noticed when reading through this is that they're flushing out the buffers before they exit. And I didn't even consider that. I was just printing out and saying that, yeah, I was in a bad state. So I probably need to modify my code to use that. I'll pull up the documentation to abort and check that it fits with what I need. Seems to be the right thing. So I modify the code that I'd written. If there's a bad state, print this, flush the buffers, and then abort. So I've got a lot cleaner code just because I jumped in, read the documentation rather than just looking at those examples or going based on what I thought that I knew initially. And then from that, now that I've got a bit of code there, the game actually crashed and it generated a crash dump because I've used abort, which was the proper thing for that abnormal state. So just to sort of reiterate a lot of that, so read the documentation, avoid just looking at examples or writing test code and seeing whether that works. This includes looking at things like language specifications or anything else, whether it's instructions that come with a compiler or whatever it is. And the next little bit of diving deep that I want to do is learning assembly. And you might be thinking, oh yeah, why would I want to learn assembly? Aside from it just being a little bit of fun. So one of the useful things that I find with assembly is it's really good when trying to debug something. And I gave a talk here a couple of years ago on expert level debugging where I had a crash dump. There was no visible call stack in it. The call stack was corrupted, but using that sort of assembly, I was able to walk back through that crash dump and reconstruct what the initial call stack was. So it's a really useful thing for that sort of advanced level debugging. It also helps you understand the compiler a little bit more. Here's a tool that I use pretty much every couple of days, which is Compiler Explorer. And with it, you can sort of throw a block of code in there, C, C++, even other languages, and it'll generate out the assembly that's used for a bunch of different compilers. You can change the compile flags, and that'll show you what the compiler's doing. It allows you to compare two different things. If I modify this code, how does that change the compiler output from that? And if you're still sort of very new to assembly, you can mouse over the instructions in this and actually look at what it is. So I've moused over the imul instruction here, and it's telling me that it performs a signed multiplication of two operands. It does. And you can dig into that deeper and right-click on it, and it gives you more context if you're after that. Another really fun way to learn assembly is to become a hacker, or more specifically, become a white hat hacker. We're not doing anything malicious. And best way to do that is get involved in capture the flag challenges. So capture the flag challenges, there's a bunch of different types of ones. Most common one that I play are Jeopardy ones, where a team will put up a bunch of different challenges and then you try and solve those. The challenges exist in many different forms, from cryptography to web to reverse engineering to binary exploitation. And for assembly, it's a lot of binary exploitation, a lot of reverse engineering. These are very competitive things, so teams are doing this every sort of weekend, jumping in, competing with each other. It's a fun exercise on top of learning, it is. And as you can see just by the calendar of things going, I think I took this screenshot in August. Every weekend there is multiple going on, there is. And if you're not wanting to jump into that competitive scene, there's also a lot of archived ones of previous years. Pico CTF's one that's targeted at high school students, it is. So you can get in, download the previous challenges, read write-ups, learn that way of getting into assembly. So just to sort of recap that, so learn assembly, good for debugging, good for sort of understanding the compiler, good for understanding performance. Not that you can look at assembly and determine performance straight away. It gives you that little bit of a hint of what things are doing. And it's a lot easier than what you think. There's no complex sort of template syntax or things like that. It's just few little instructions and then a few operands applied to it. And the more that you read it, the more that you get comfortable with picking up patterns, and you'll be able to read it much quicker. And you don't need to learn to write it, just learn to read it. It's the easiest thing. Then I also want to promote people sort of change their viewpoints. This is a little bit off the track of assembly. And one viewpoint, I was thinking, what's a viewpoint that a lot of people have that I could potentially sort of get people thinking outside of the box? And one thing that I came up with is exceptions. So I'm sure many people here have a dislike of exceptions. I'm sure one of the things that someone's probably thinking in their head, no, they are slow. Do not use exceptions. Get them out of here. And I think that is the case in only when we're actually throwing an exception. But if we're actually not throwing that exception, it's not slow at all. It's potentially faster. So I guess that comes down to when should an exception occur? And my viewpoint is they should never occur except in exceptional circumstances. So this is really, if for a game, are we exiting right back out to the menu? Like that menu loading cost is going to be much more significant than what it is just throwing that exception up and letting it bubble up to wherever it needs to be. So this is the viewpoint that I take on when exceptions could potentially be used. I'm not saying you should use them, but this is more just an example of changing your viewpoints on things. So I guess what's the performance of that sort of overhead and how does it look different? So here I'm just going to go through a few different compilers and different ABIs and just see how exceptions really look if we're taking that viewpoint. So I'm starting out with a function that just divides one number by another number, and the assembly for it is really just 3 instructions there. It's very simple. If I want to modify that, so then we don't allow allow it to be divided by 0, and instead we throw a division by 0 exception. The code that we get for that, it looks a lot more than what the initial code is, but if we focus only on the success part of that, then it's really just 2 extra instructions. All we're doing is just testing that number, see whether it was 0, and then if it wasn't 0, then we jump down. So it's 2 instructions, very lightweight. But if we're comparing exceptions, we need something to compare against. So let's compare it against using ST optional. So here we've got the same thing. If it was 0, we instead return a null opt, which is an optional that's got nothing inside of it. And if we look at the code for it, we can then do the same thing. We'll exclude the bad case for it. It looks like it's got a few more instructions than what the exception one has. It's got particularly this move ABS, then an OR in that. That's because the optional actually has to store extra state to indicate whether it's successful or not, where the exception's got a completely separate path. And this was just looking at CLEG and the System V API, which is the Linux one. So let's take a little bit of a quicker look at the Visual Studio one and the one that comes out of the Windows ABI. So again, we've got the same output, a little extra move there because of the operands that are passed in. The ABI requires different argument registers. The case for using exceptions, it's a little bit more, it is. So we've got an add and subtract of the stack, so it needs a little bit of stack space whenever it's dealing with exceptions. But if we compare this now to the optional case actually had, here we've got a branch at the start where it actually expects that we're going to hit that optional case, it does. So as we can see, when I switch back and forth between that, the little snippet that's disappearing is actually the case where it's expecting us to go, it is. And the reason why we typically want code to flow in the success case one after the other is because if this code's only being seen for the first time, we're not going to have all the instructions loaded, so the instruction case is going to read in block by block. And then also branch prediction. So with the branch prediction, there's 2 sorts. There's static branch prediction and there's dynamic branch prediction. And static branch prediction is often used when the CPU is seeing the code for the first time. It is, and the typical way in which it works is if you've got a branch that goes forward, it's assumed that it's not taken. If it's a branch that goes backwards, then it's assumed that it is taken. So this is handling loops and handling if statements. So in this case, it's probably going to assume that it wasn't taken unless the compiler's caught up to that in with all of the arguments there relevant, which could depend on whether it's from memory or something else. So it's not quite as optimal as the exception version, and it's also got this little bit of extra storage here in a temporary register that's used because an optional is a little bit too big for just fitting in registers it is. So there's a bit of overhead there. If we look at the other side where we're sort of trying to catch this exception, the code for it, again, we'll focus just on the success case for that. It's just sort of pushing a pop of unused registers there just because it needs a little bit of stack space, and it's a direct call. We compare that to the optional. We've got a few more extra instructions there. So we can see that optional is starting to look like it's more expensive than exceptions it is, at least just looking at the assembly side of things. And then if we look at the Windows version of that one, similar sort of thing, but we've got a little bit of an odd thing here where it's got a call to the function, then it's jumping over. So it's got a sort of unconditional jump over an XOR here, which is that sort of returning 0 from when the exceptions occurred. So not quite like the optimal code that we'd want, but that should be hopefully fairly efficient for that. But if we compare that to the optional version, we've got a bunch more extra instructions here where we're doing sort of an XOR, comparison, and then a conditional move. So there's a bunch of little extra work that we're doing, just avoiding exceptions for these cases. So taking all that into account, did we potentially focus too much on the performance of the bad case with the exceptions? And I think that could be the case, but I've got a slightly better answer for why we've got this sort of ingrained view that exceptions are bad. And that's because 32-bit exceptions were extremely bad, even on the success case. And to sort of just show some examples of that, if I've got that same sort of try-catch block here, and the try-catch block you can see is significantly larger than the optional one. It pushes a bunch of things on the stack, pops them all back off. It's storing a whole heap of things that we really shouldn't need to store. And then if we look at another case where exceptions impact things, is if we just had a function that has an object that has a destructor, it also has a bunch of things that it needs to sort of push onto the stack and store those. So this is where exceptions were very costly in that sort of 32-bit stage. But now that we're on 64-bit, potentially we should reevaluate those things and change our viewpoint that we had on exceptions. So just to recap some of that, so always dive deeper, read the manuals, specifications, don't be afraid of jumping into assembly and sort of avoid that sort of hive mind thinking or following your peers or whatever influencers say about sort of different things. Dig into stuff, look and see whether it's potentially still the case if someone's sort of raising some concerns or has interest in it. So now on to performance. So performance is not just about sort of counting cycles. There's all, like, you really want to try and do less work. It's the best way to get the best performance out of things. Partition stuff over multiple frames or even over multiple threads wherever you can. And as we start sort of looking at sort of parallelism and concurrency, one thing I commonly see people reach for first is mutexes. And to me, as soon as you're starting to reach for mutexes, it's a bit of a code smell. And then as soon as you're reaching for lock-free, it's also probably another little bit of a code smell it is. Because all you're doing is changing that sort of multi-threaded code into a bunch of serial code. You know, so it's not actually gaining the huge performance gains. It might be a little bit of performance gain, but probably not what you think it'll be. So one sort of approach that I like to look at is how can I look at that thing that I'm trying to make parallel? Can I make it sort of a parallel for loop? Is each iteration of a loop completely independent? Or is the data independent enough that we can do everything and then at the end we consolidate it all? So parallel for loops are the first thing I go to when I'm after a little bit of concurrency. And then I think a little bit about data dependencies and scheduling. So if we look at, say, a standard function where you pass in arguments and then you've got return values and then you pass that return value onto something else, if you've got functions that are only taking in sort of arguments and they don't mutate any other state, then you might be able to run those two functions at the same time. So really sort of build out a graph of data dependencies that exist to avoid having to lock anything, because if nothing's writing to the same data or writing at the same time as reading, you don't need to worry about mutexes at all. And then lastly is when you start looking at those adding locks or using lock-free. But then there's the fun part of the micro-optimizations, and This is where I'm going to dig into a little bit deeper, where micro-optimizations can be seen as sort of a sequence of data dependencies also. So CPUs do a lot of work out of order, they do. So for this example, I'm going to use a linked list here, and people are probably fairly familiar with linked lists. I often think of linked lists as sort of having this the head node that iterates through everything, and then there's probably a null for the next and the previous. The linked list I'm going to work with for this example is a sentinel-based one, where instead of those null pointers at the start and the end, it's got the head node is just a sentinel that has its own next and previous. The tail has its own next and previous, and this allows for more efficient inserting, allows for a little bit more efficient iteration, it does. And what I'm going to do is I'm going to take a bunch of numbers. In this case, I've just thrown in 10, 32, 47, and then I'm going to sum all of those numbers together. So this will typically involve sort of starting at the head, moving through each item, and then iterating and adding each of those. And the code for it is a very basic loop here, where we've got sort of we get the begin node, we get the end node. And if we're not at the end, then we're going to get the value off this. So this is just an integer that we're adding up. And then we're going to add that to result. And then we're just going to move to the next item. And then we finally return the result. So again, just to get people a little bit more comfortable with looking at assembly. The main thing that we're after here, everything's going to be mainly in that loop. The rest of the code we don't need to worry too much about. So let's just focus on that. And we can see that this is nearly a one-to-one mapping. Like there's 4 instructions there for what is essentially 3 different lines of code. So we've got one bit here that's just doing that check if we're at the end of the loop. There's a little bit of a check before, but this is the main part that exists inside the loop, so it's doing it at the end for the next iteration. We've got the part that's adding one value onto the result. So this is just stored in a register. It's doing a load from memory there at the same time. CPU will extract these out and be 2 different micro instructions they will, but for our case, we're just looking at the x86 assembly here. And then we've got the moving to the next item we are. So, what are the data dependencies here, and how will this look to the CPU? So first off, we've got these sort of the begin and end pointer that we're using, and the begin pointer we're storing in iterator because we're going to keep changing it. We do. And the first iteration of it, we're going to look at the CPU and how it takes it. So the CPU is going to read in blocks of instructions. It won't necessarily start executing all of that. Like it's not going to finish each of these in one order, it isn't. It'll fetch out groups of instructions. So it's fetching out potentially 1 iteration of this loop, fetching out 2 iterations of this loop, and this might be before it's even read that data from memory. It might have queued up that it's going to read that data from memory, but because of branch prediction, it's going to predict that hopefully that loop is going to keep going. It is, so it'll queue up these sort of set of instructions, but that doesn't mean it'll start doing it. It'll only be able to start doing it if all of the dependencies that it depends on are there. So if we look at sort of that first little instruction that we were doing, where we're sort of fetching that begin pointer, as soon as we've fetched it, the first iteration of the while loop can start, well, it can't quite go till we've got the end iterator, but it's got one of its dependencies there. The fetching of the value and adding it to result can start going. So it hasn't fetched the result, but it can start at least doing that step. It can start looking for the next pointer to update to. And then we've got the end iterator there, which allows that while loop to also get all of its data there. There's also the dependency that exists with result, but that's really just a register, so I haven't highlighted it very heavy. But in order for the next iteration to continue, we need that final instruction there with the iterator equals next iterator to complete. And once that has completed, then it can start doing things. So we're really just doing these blocks of sort of 3 or 4 instructions, one at a time, which is heavily based on memory. And that memory for a linked list might be scattered all over the place. It might be all within sort of the L1 cache, might be within L2 cache, or might be way out in main memory that it's got to fetch from. And that's one of the downsides of linked lists, is that it's the memory where it lives is very out all over the place. It is. And we've got sort of that next iteration of this. And this is very inefficient. So if I wanted to change this thing and sort of look at how I could potentially make this a little bit more parallel, and I don't want to change the data structure at all, I want to still keep a linked list, there's a little sort of secret approach that I discovered when I was just writing this talk that I figured I'd try out is, instead of just iterating it forwards, what about if I iterated it backwards at the same time? So I'm adding from the front, adding from the back, and then somewhere in the middle I'll meet. And so I'll add this little bit of code here where if I'm not at the end, then I'll move in one from the end and I'll add that result in there. And the code for it is just a few extra instructions It sort of ended up placing the first bit of that code is actually the end iterator part. The second bit is the forward iterator part. It is, but if we look at the dependencies of that, we haven't changed any of the dependencies of the initial code except for one little bit in there, which is that while loop. And again, that has the branch predictor, means that we're not going to be blocked on that. But if we throw in our new block of code, the link between the two is just the end iterator there that I mentioned, but it's got its own dependencies on those initial variables, and then it's got its own dependencies for the next iteration of that. And it's also got that dependency from the other direction of forward, but these again are only on branches, so branches, the branch prediction handles that. So if I do this version and I compare it to the previous one, I actually end up 1.9 times faster. So we've just optimized a linked list iteration to be nearly twice as fast. And under these unrelated results, I've got sort of a bunch of other things that people probably had ideas that, how would I optimize this code a little bit? And one of the first ones of those is prefetching. I keep seeing people throw a prefetch into a loop that's iterating through a linked list. That had no actual impact when I threw in a prefetch in there. When I prefetched 2 levels deep, didn't have any impact either. If I threw it in an array, yep, that blew it right off the shelf, it did. Ended up significantly faster. It even auto-vectorized it in the compiler that I was playing with. If I remove the auto-vectorization, still massively faster. So yeah, we can optimize even a linked list, but vectors are still much faster. But it's just understanding those data dependencies allowed me to improve that algorithm. It did, and that algorithm has existed for ages. And my guess is no one here's probably heard of iterating a linked list in both directions at the same time. And if I take that a step further where I'm not just adding values, what about if I find values? So this is just doing a search in a linked list. I had probably about 1,000 items in this, just finding a random item in there. And it again was 2 times faster. You might be thinking, oh yeah, that's from the start and the end. What about if we try from the middle also? So I threw in something where I tracked the middle of the linked list and I went outwards at the same time. So I'm going inwards from both sides and then I'm going outwards from the middle. So I'm doing 4 times this, and I end up 4 times faster because the CPU's got enough room there that it's processing through those. So that's enough on the performance side of things. I'll jump now into sort of some software architecture. So one thing I commonly sort of hear people say is, how do I test games, or it's really hard to test a game, it is. So one thing that I like to approach if I'm testing something is build out libraries and helpers, because libraries and helpers are much easier to write a unit test for. I don't need my whole game spun up. I don't depend on some other functionality that someone's written for the game to launch for me to get anywhere. So if I look at a game of Tetris and I was like, oh yeah, what could I break out in terms of helpers and libraries there? We've got the random choice of the block. I can break that out, make it its own function, write a quick little unit test for it. It's reusable in the next project. I've already tested it. I've got block collisions. This is a little bit sort of specific to the game, but I can write the unit test for that. So if someone goes to modify that code later on to add some extra edge case, they're not going to break the edge cases that I've already considered. Wall collisions are the same thing. Time is another one that can be shared between projects that I can write sort of tests for. Then there's just the active block rendering. So there's a lot of little parts that come together to make that game that can be tested independently, they can. And all of those parts together can then make the game that I want. And then if we go something a little bit more exotic that is probably a little bit harder to consider testing is, what about the input capture? So we've got keyboard, we've got controller, whatever sort of inputs that we want. If I wanted to test that, what I would do is still build out libraries for it, but I would build a separate application where I've just got my own little isolated sort of sandbox where I can test those operations I can. And that way I don't need this full game spun up. I know that I've got specific tests for it, and that allows me to quickly iterate through that. It does. And I don't need, like sometimes a lot of our games probably take a long time to spawn up, and I don't want to depend on that either. So the next thing I want to sort of harp on it about is make things that are easy to use correctly and hard to use incorrectly. So if we look at this sort of thing here where I'm creating a date, I'm sure no one actually knows the final date that I'm after for this. Someone's probably thinking, 6th of October 2025. Another person's thinking, July 10th, 2025. And then someone at the back's probably thinking, this is the 2025th of October, 6 AD. It's my typical view on it. But if I was to slightly change this and I instead had a date where I've wrapped these in sort of strong types, so I've got a strong type there for the day. I can see that that's day 6. I've used an enum for the month. I can see that that's in October and the year 2025. So now if I go around and ask those same 3 people again, 6th of October, October 6th, and 6th of October also for the next one. Or they might say 2020, they might jumble it around however they like. So this is just one example of sort of building those easy to use interfaces. And then a little bit more complex example is I've got a concurrent queue here where I've got sort of a push function where I can push in items into that queue. Another one where I can pop items off that queue. And if I go to pop items and the queue is empty, then it'll block at will until there's another item added. And then I've got another thing there where I can check whether that list is empty. So it's just a Boolean that just returns whether it's empty or not. This interface to me is very easy to use incorrectly. And can anyone spot why this might be hard to use? Can spot the issue? No hands, but if I show this example, and we've got 2 threads potentially doing this, while the queue is not empty, we're going to pop things off the queue and process those items. We've got 1 thread that's doing it. It's going to pop those off successfully. It's only ever going to see the queue empty. If I have 2 threads that are now both checking if it's empty, they both check it's empty, then they both go to pop, one of them's going to end up blocking. So our process non-blocking is actually blocking off and on depending on what's happening. So a better interface for this is actually to go and use try properties to make it so we've got something there to try and pop that, and if it popped it, then we return a value in an optional. And this little change means that we can write that process non-blocking. It'll be safe to use, and someone's not going to incorrectly use the interface because they don't think of concurrency the same sort of level that I might think of it. So just to sort of recap a lot of that, so for software architecture, build libraries and helpers. It makes it much easier to test. Write easy to use, correct interfaces. The interface is often a lot more important than the implementation because you can change that implementation later. But the other thing to consider is the more widely used that your interface is going to be, that's when you really need to consider it. Spend a lot more time on that interface to work out, is someone going to use this incorrectly? And can I work around them, prevent them from using it incorrectly? Now, the old one is focus on sort of sane restrictive defaults to start with. And then on to any questions. I was putting the questions in the app, so I need to just bring up the view. Has anyone added anything to the app? Well, no. Does anyone have any questions they want to ask with the microphone while I pull up the app?
Arguably, like a lot of these changes could potentially make the code less readable, harder to update in the future. So, like, where do you draw the line between introducing that performance and making it easy to edit?
That's where I take the same approach. If something's going to be hard to use or hard to maintain, put it in a library somewhere. Hide that hard to maintain part. Like, if you need the performance, then you need it. So you want to hide that. Have a good interface where it is easy to work with, and just isolate the few people that are allowed to work on the hard to maintain part.
Thank you.
Yeah.
Don't know if I'd fully formed this question in my head before I put my hand up, but I think the example with the double linked list there, I was trying to understand your thought process because it was super awesome, but I don't know how I'd replicate that on like a slightly different problem. Is it that you sort of look at what data dependencies that you have, and then look at what other data you have to play around with that could help with the problem? Is that sort of where your thought goes?
If I've got a problem where I've got something that, like, it could even just be a function where I might have, say, I'm doing something and then I divide by another number. Like a division's a really long operation, and how can I break that dependency out? Can I move it out of the loop? Like this example here is very similar to loop unrolling, where you do two things at once. Not everything is that easy to sort of break out, but it's really looking at the dependencies, looking at is there more room for me to do two things at once here while I'm doing one thing, and then if you can make a helper around that, like you might be able to do with linked list iteration, then all the better.
Awesome, thank you.
What are your favorite tools for looking at the behavior of the branch predictor and the prefetcher and stuff?
So a lot of that depends on the platform that I'm working with, but I'm really looking at sort of the performance counters for that platform I am. So first off, I'll isolate, this is something that I want to look at. This is something that's got a performance impact. Then I'll turn on sort of some performance counters there, where I might sort of look just at a high level view. Is it front end bound, back end bound, and then work out, is it something that I need to worry about with memory? Is it something that is just too heavy on sort of all the execution units within the processor? Is it something that's the branch predictions just going all over the place, and sort of digging at that level it is. So there's a approach from Intel that's sort of this top level down viewpoint of that sort of micro optimization that's well worth digging into.
When building game-specific functions and helpers, what's your thought process on breaking down like the problem and then building those functions and helpers? Like for example, in Tetris, how did those answers come out?
For that one, it was more just thinking about, what are things that I can break apart here. And for Tetris, you might not go that fine-grained. It was more just an example, but sort of think about the things that this is something that could potentially break or I could get wrong, and then make those helpers, or something that I might reuse, then I'll make a helper for that. So not everything has to be a helper, but building those libraries and helpers does make it easier to test.
I'm going to assume the date thing was kind of just an example you made, but I have seen code that kind of looks like that, and have been on both sides of the debate of like, is this too protectionist? Of like, do I want to bend over backwards to prevent people from using my code incorrectly? Kind of like towing the line between trusting my team to not be stupid with my code. Because yeah, I've seen it go so far as some people restricting their like what size an array can go to in their code. I'm like, I think that's a little too far. Like what are some like, I guess, good like heuristics or ideas you have around how far one should take that?
Yeah, I think it's definitely case by case. No, like you've also got to consider the fact that if you go too heavy in some of that, then it's just layers of abstraction that also add overhead. So it's that balancing act and just finding what's right for the code base, what's right for the team. Like if you've got a small team where everyone, like you can just reach over and talk to the next person, and you've got heavy code reviews, you're seeing the code very frequently, you probably don't need sort of that same sort of restrictive environment, but you're also your own worst enemy. I've written code for an interface. I've tried to use interfaces that I've written ages ago, and then I misuse them myself. So I don't trust myself when I use my own interfaces. So.
Where do you go for those capture the flag type challenges?
So the place that I typically go for it, so let me just go back to that slide. There's a website called CTF Time, and CTF Time has sort of the list of all the different challenges it does. So hard to go through all these slides again. Too many slides. But on CTF Time, you'll find the list of the ones that are upcoming, and then you'll find the calendar on there that you can look through. And I'd recommend just trying it once, even if people are sort of not wanting to get into that security thing. It's still just a fun exercise to do. It is just get a group of people together, jump in, try it for a weekend, and like as you can see on here, we've got you've got the upcoming events, you've got the past events, and the typical thing that a lot of people do when they get involved in these CTFs is people that solve the challenge and manage to solve them, they'll post a write-up, they'll explain how they solved that challenge. So that way you can learn when you were stuck on it how someone else solved it. If there's any other questions, feel free to ask me in the hallway.